Hello. I will explain more rigorous definition and how we show identification more rigorously. So we need to learn a few more preliminary concepts. First, we have to understand data generating process. DGP, often it is called DGP, and DGP is literally how the data are generated. So our job is looking at the data and recover the underlying parameters. But obviously, before the data are observed, the data must have been generated from the model. So originally, there is a model, and the model generates data, and we observe the data, and we would like to recover the model again. That's how we imagine the data are generated and what we are doing. So the data generating process is exactly what happened. The data, what would happen before the data are observed. So suppose that there are parameters. Say the Mother Nature determines the parameter values, true parameter values, and from there, exogenous variables and error terms are generated according to the assumptions. Of course, they satisfy the assumptions and also they satisfy the true parameter values. So the exogenous variables are generated, and then based on those exogenous variables, they are put into our model according to your assumptions. And then according to the model, endogenous variables are generated. So they are determined by the model and by the exogenous variables. And after deleting unobserved variables like error terms, we observe the data. That's how the data are generated before we observe. So in the linear regression model, it's obvious. So first, someone chooses the true parameters beta and sigma squared. And then x, the independent variable x and the error term epsilon are generated to satisfy those assumptions like exogeneity assumptions, invariability assumptions, and homoscedasticity assumptions. So x and epsilon are generated, and then based on those outcomes, y is determined. Y is generated according to the linear regression relationship. And then finally, epsilon is deleted. Of course, beta is not observed, and we only observe x and y. That's how the data are generated from the model and the parameters. It's intuitive, just terminology. And what's more important, so this is more confusing and more important concept, observational equivalence. Imagine there are data generating process. So there are different data generating process, which means different values, say beta equals to 1 and beta equals to 2. So those two are different data generating processes. So when beta equals to 1, you have this data, and beta equals to 2, then you have different data. But in some strange cases, different data generating processes may result in the same data, right? So that is, we refer to this case as two data generating processes are observationally equivalent, right? Suppose that there are two different values, beta tilde and beta 0. So beta 0 is the true parameter, and beta tilde is a different value. And now imagine that you generate x and epsilon according to the assumptions, and generate y tilde using a wrong parameter value. So the data are generated in the same steps, but we use a different parameter value, and we observe y tilde and x. Y tilde and x tilde. And in some cases, in linear regression model, it is not possible, but in more complicated examples, even though beta 0 and beta tilde are different, still the observed distribution could be the same. That's possible when the model becomes more complicated. In this case, beta 0 and beta tilde are observationally equivalent. And in that case, from the data, we cannot distinguish. So two data generating process generates the same data. Then from observing this data, we don't know whether this data is generated from here or there. So we cannot distinguish what is the correct data generating process, what is the correct parameter value. So in that case, we say beta is not identified. That is identification failure. So, and in this case, I assume that the number of observations is unlimited. So you observe infinite number of observations from each data generating process, but they can be the same. So this is a problem. So so this is when we cannot identify beta, and some basic identification rules. So the simplest case we consider here is if you observe a random variable, its distribution function is automatically identified, right? So you observe random variables for an infinite number of times, then if you make a histogram, then the histogram will converge to, in the end, if the sample size is infinity, the histogram will be its distribution function. So it's obvious, right? So, and rule number 2, suppose that you identify an object, and then anything that is uniquely determined by the object is also identified. For example, you observe x, so you identify the distribution function of x. And then expected value of x is uniquely determined by the distribution function. So if you know the distribution function, almost everything is identified by the distribution function, so they are also identified, right? And when you observe the joint two random variables, their joint distribution is identified, and from the joint distribution, you can uniquely determine their marginal distributions, conditional distributions, and their mean and their variance, their covariance, right? So this is the simplest possible cases. So you may simply say that because we observe x, its expected value or its a distribution function is identified. So you are going to see the argument more later. Let me show you how we can rigorously show the identification of beta in the classical linear regression model. What you need to look at here is pay attention to how those assumptions are used. Actually, we do not use the fourth assumption, but other than the fourth one, we are going to use the other three very carefully. So, and basic idea is we will show that beta, so from the beta, the solution to beta can be uniquely determined by the data. So let's see this. From assumption 1, linearity assumption, pre-multiply x to both sides. So then you have this. So x, I, y, k by 1 vector, and k by 1, 1 by k, k by 1. So k by 1 vector, and k by 1, 1 by 1, k by 1. So multiply x on both sides, and take expectations on both sides. So expected value of this, expected value of this, expected value of this. And remember, beta is non-random. beta is not random, so beta can get outside of the expectation. And also remember and also remember that by assumption 2, by the exogeneity assumption, this guy disappears. It equals to 0. This equals to 0, so there is no there is no error term at the end. And by assumption 3, you can take inverse of this guy. So this matrix has an inverse, well-defined inverse. So you can multiply the inverse matrix on both sides so that on the right-hand side, only beta is isolated. So this is the unique solution for beta 0. So I've already shown that this is unique. And the reason why it is unique is if you observe an infinite number of observations of x and y, then you can uniquely calculate x and y expected value. And also expected value of x prime inverse, it can be uniquely calculated from your infinite number of observations. So these so the infinite number of observations can uniquely identify the expected value, so it's obvious. So once you have these two guys uniquely determined, then beta is also uniquely determined by multiplying them. So beta is unique. That's how we prove identification. So this is too simple. You may think it's too simple what we are doing, but the basic idea is uniqueness of beta. And when you can write a parameter in terms, so this is the parameter, you can write the parameter in terms of identified objects. So this is identified, and it's a function of identified objects. Then the parameter is identified. So simple. So it means that you can just calculate expected value of xy, expected value of xx transpose, then you get beta. So it's uniquely identified. And assumption 4 is not used because the assumption is mainly for central limit theorem, which will be used later. And let's think about identification of epsilon. Of course, epsilon is not observed, so epsilon itself is not a parameter because epsilon is random. But for example, if you'd like to identify the distribution of epsilon, such as variance, then how can we do that? We observe y and x, and we identified beta. So epsilon is identified, and so y minus x transpose beta 0. When beta 0 is known, this guy is also identified, so this guy is also identified. Epsilon is identified. So from the identified epsilons, you can identify its distribution. So when you know x and y, then you know beta 0. Then beta 0 from x, y, and beta, you can identify epsilon. And from infinite number of epsilons, you can identify its distribution. So everything is identified step by step. So when you see the proof for identification, it looks too trivial, obvious. Everything is obvious. What's the problem? So later in the next lecture, I'm going to show you two most popular examples of identification failure, right? So identification failure will help you better to understand identification concept. So I hope it makes sense to you, and see you in the next lecture. Bye.